Let's continue the ZAERO advanced training with section 4, closed loop ASE. So we'll look at the bulk data cards here for the ASE closed loop analysis. For the closed loop analysis, as compared to the open loop analysis, you must additionally define bulk data cards which specify the control system and the gain matrix. So we have the ASEGAIN card, which defines the control gains. And then we have the CJunct, which defines a generic MIMO junction control element. The CMARGIN card allows you to specify parameters for control margin analysis. The CNCTSET card lists out the fixed connection cards, refers to those. The CONCT are the fixed connections, so that defines those. EXTINP and EXTOUT define external inputs and outputs, which of course do not affect the stability of the system. The GAINSET card refers to a set of ASEGAIN cards to enumerate them. The MIMO SS is the definition of a MIMO controller, and the CISO TF allows you to define a CISO transfer function. The TFSET lists out the set of transfer functions you have, and then finally the PLTBODE card allows you to create a file for plotting the Bode response of the system. So first let's review the feedback sign convention in ZAERO. Classic control methodology generally assumes negative feedback from the controller to the plant. So if you have a control engineer that on the right hand side here designs a controller and they just give you the ABCD matrix of the controller, they may be assuming negative feedback, which you'd have to clarify with them. However, in the ZAERO closed loop modeling, it's made up of fixed connections and gain connections between all of the control elements, which results in a positive feedback convention. So a controller designed with a negative feedback assumption can be incorporated into ZAERO by different methods. First, you can add an ASEGAIN card with a gain of -1 to connect the controller to the actuator. You can modify the controller itself to assume positive feedback, or you can add the negative sign at any other suitable location among the ZAERO control elements. So on the left-hand side, we have the ZAERO convention. So on the top left, you can see everything has positive feedback, so this controller must be designed with positive feedback. If the controller itself is designed with negative feedback, then you can put the ASEGAIN card in between the output of the controller and the input of the actuator. Next, we'll look at the bulk data interrelationship for the closed loop ASE analysis. So once again, we have the ASE card, and the additional cards come into play here through the ASE controller bulk data card, where we define the control system elements here through the TFID field, the CONCT ID, and the gain ID fields. Additionally, the CMARGIN and PLTBODE cards can refer to the ASE card to have additional output from ZAERO. So next we'll review how to connect different control elements. So control system elements consist of two types. We have functional elements and connector elements. In this diagram, functional elements are outlined in black and connector elements are outlined in red. So the functional elements include the ACTU, which is the actuator definition, ASE sensor and ASE sensor 1, which are the sensor cards, the CJunct, MIMO SS, and CISO TF, which are control elements. And the CJunct and MIMO SS elements may have more than one input and or outputs. And then the connector elements include the ASEGAIN card, the fixed connection, CONCT, and external input and external outputs. So in this example here, we have two sensors. In our model, we have 3 actuators, and then additionally we have an external input, which could be, for example, a pilot input command. So our first ASE sensor here is connected to a MIMO control system through an ASEGAIN card, and then additionally the external input feeds directly into the control system. The output of this MIMO state space control system, we have three outputs. So the first two outputs are fed back to the actuators via the fixed connections, and then the third output is an external output, which you can use for measuring. So this can be some internal state variable in the control system or some variable of interest that you're outputting from the control system. You could even copy the output to one of the actuators into this external output. And then next here, this sensor, the second sensor is connected to the CISO-TF via a fixed connection card, and then the output of the CISO-TF is connected to the actuator through an ASEGAIN card. So you can see here, what I recommend is to draw out all of your control elements that you have in the model, so then you can make this diagram that we have here, and you can easily see how to connect all of the elements to each other using the fixed connections or the ASEGAIN cards. So the ASEGAIN bulk data card is shown here. So this defines the control gains for the ASE control system. We have an ID number, and then next, the OTFID field is the identification number of the upstream control element, defined in the CJunct, MIMO SS, CISO-TF ASE sensor, or the ASE sensor 1 bulk data cards. So the output of that control element is the input into the ASEGAIN. The next, the CO, is the output component of that control element. For the CISO-TF, or the sensors, the output component would be 1 because there's only one output. For the CJunct and MIMO SS, those can be multi-input, multi-output control elements. So the CO field allows you to select which output of that control element is connected to the ASEGAIN card. Next, we have the ITFID field, which is the identification number of the downstream control element, defined in either the CJunct, MIMO SS, CISO-TF, or the ACTU, the actuator, bulk data cards. And then likewise, the CI field is the input component of that control element. So once again, the CISO-TF and actuator only have one input, so CI must be 1. For the CJunct and MIMO SS, as those are multi-input, multi-output elements, you select which input through the CI field. Next, gain can either be a real number or an integer. If gain is a real number, then that gain is the gain value of the connection. So usually that would be 1, but you could adjust the gain as needed. The next option is if gain is an integer, then gain is the identification number of a table D1 card where the variable gain is specified. So you can define a variable gain scheduled on either, and if we look at the type, it could be scheduled on velocity, density, dynamic pressure, or altitude. So what happens here is during the simulation, at each particular time step, during a time domain simulation, or for the stability analysis, you look at the flight condition as you're computing the eigenvalues. You look up the either the velocity, density, dynamic pressure, or altitude, and we use the table D1 card to look up what the gain value is for that particular variable. And of course, the altitude only works if the fixed MATM card is utilized where you specify flight conditions as function of altitude. So remarks, all ID numbers of the ASEGAIN cards must be unique. The ID is referred to by the GAINSET card, and then the gain defines the terms in U equals G times Y, where G is the gain matrix. Next, we have the CJunct card, which is a multi-input, multi-output matrix where Y equals DU. So we have an ID number, and then our NU and NY fields determine the number of inputs and number of outputs, and then the DIJ fields are the elements of DI. And note that, like Fortran, it's specified in column major order. So if NU, for example, is 2 and NY is 2, then the order is D11, D21, and then D12, D22. And once again, all ID numbers of the actuator, ASE sensor 1, C-junct, MIMO SS, and CISO-TF must be unique. So these are the functional control elements. And the ID is referred to by the TFSET card. Next is the CMARGIN card, which is the control margin analysis parameters. So this defines the ranges of interest for finding gain margins, phase margins, and singular values in the ASE analysis. So SID is the set identification number. UGM is the upper limit in decibels in search for the positive gain margin. LGM is the lower limit in search for the negative gain margins. UPM is the upper limit of the search for positive phase margins. LPM is the lower limit of the search for negative phase margins, and those are in degrees. And then USVI is the upper limit of the search for the input MIMO margins in terms of smallest singular values, and USVO is the upper limit of search for the output MIMO margins in terms of the smallest singular values. Next, the ID frequency field is the identification number of a frequency or frequency 1 bulk data card, which specifies the frequencies in hertz where the MIMO singular values are computed. And if this value is 0, then the structural natural frequencies are used. Next, we have the EPS field epsilon, which is a tolerance used during margin analysis to decide if a complex value is a pure, imaginary, or a real number. Method is a flag field that's an integer to define the method for the frequency domain CISO margin stability computation, and it's not used for the state space form. If method equals 0, which is the default, then the G method is used. If method is greater than 0, then the modified PK algorithm is used. And then lastly, adapt is another flag field. This is an integer to define if the adaptive algorithm is used during the frequency sweep process for the frequency domain CISO margin stability computation, and it's not used for state space form. If adapt is 0, which is the default, then no adaptive algorithm is used. If adapt is greater than 0, then the adaptive algorithm is activated. So a normal frequency sweep is conducted first, and then the initially obtained cross frequencies are added into the frequency list to search for the final results of the cross frequencies. Next, we have the CNCT set, which defines a set of connections of transfer functions for the ASE analysis. So this card is referred to by the ASE controller card, and then it simply just lists out the identification numbers of the CONCT cards. So we have the CONCT card, which defines the fixed connections. So this is very similar to the ASEGAIN card, except we don't specify a gain. The connection is just a fixed connection, so the gain value would be 1. So we have the OTFID, which is the identification number of the upstream control element. CO is the output component of OTFID. ITFID is the identification number of the downstream control element, and CI is the input component of ITFID. Next, we have the external input card, which defines the input of the control element as the external input of the ASE control system. So the ID number is the first field. Next, we have type, which is ignored, it's not used. And then ITFID is the identification number of the downstream control element, whose input is the output of the external input element. CI is the input component, and then label can be any alphanumeric string of up to 8 characters to describe the external input. So an example here is shown in remark 2. So we have a C-junct card. Well, first let's see, we have a sensor, we have some sort of filter or control element, and then we have an actuator. Meanwhile, we want to add in the external input. So this could be like a pilot input command supplemented or augmented by a some sort of filter or control system. So the way we do that is define a C-junct card, which is the control junction element, and this could add, for example, the first and second inputs and feed that to the actuator. So for this card, the ITFID is 400, and then CI is 1. Next is the EXTOUT card. This defines an external output. So we have the ID number. Type, once again, is not used. OTFID is the identification number of the upstream control element. And CO is the output component of that element. And then, once again, we can have a label, which is any alphanumeric string of up to 8 characters. So in this example here, we want to see what the output of, for example, this filter is. So we have a C-junct element control junction which splits the signal from the filter. So for example, if the C-junct D matrix is 1, 1, it just copies the output of the filter to both the actuator and the external output. So this EXTOUT card OTFID would be 400, and then the CO would be 1. Meanwhile, you would need a fixed connection card in between the C-junct and the actuator, which is not shown. Next, we have the GAINSET card, which defines the set of gains. So this is referred to by the ASE controller card and then lists out the ID numbers of the ASEGAIN cards. Next is the MIMO SS card, which defines a MIMO control element. So we have an ID number. Then next, NTF is the order of the controller, which is the number of states, which is the size of the A matrix. NU is the number of inputs. NY is the number of outputs. And then NL-MIMO is the label of a matrix name. And that matrix can be input into ZAERO either using the DMI bulk data card or using the assign matrix executive control command. And that matrix is a combination of the ABCD matrices as shown here. And then ZAERO will parse out the full matrix to extract the A, B, C, and D matrices based on NTF, NU, and NY. Now, if L-MIMO is blank, then a variable MIMO element is assumed, which functions the same as the ASEGAIN card where we have a variable gain. So then the entries type PRNT, XI, and LI are required. So we'll look at how that's defined next. So type specifies the type of interpolation. So it can either be velocity, density, dynamic pressure, or altitude. So that's defines the type of scheduling that our controller is using. PRNT is a flag to control printing out the variable MIMO element matrices to the standard output file. If PRNT is 0, then the matrices are not printed out, and if PRNT equals 1, then the matrices are printed out. And then next we have an open-ended input to list out the ABCD matrices at the discrete points. So XI are the X values of the data pair, and LI are labels of the matrix names, the ABCD matrices. So if we go back here, you can see we have X1, L1, and then X2, L2, X3, L3, and so on and so forth. Of course, the matrix size must be dimensions NTF plus NY by NTF plus NU. Next is the CISO TF, which defines a single input, single output transfer function. So we have an ID number. The next field, NDEN, is the order of the denominator, and num is the order of the numerator, and where NDEN must be greater than NNum, which must be greater than 0. AI is the coefficients of the denominator polynomial, and then BI are the coefficients of the numerator polynomial. So the transfer function is given here in remark 4. So you can see the bi's are the numerator, where bi goes from b0 to bn num, and in the denominator, the ai values go from a0 to a n-den minus 1. Finally, n-den can be 0, in which all of the remaining entries are ignored, and a zero-order controller is defined with a unit gain. This option really will only be used in the case where you have a grid force bulk data card to define a grid force, which refers to a CISO-TF card to define the transfer function of the actuator of the grid force. Next is the TFSET card, which lists out the control elements, the CJunct, MIMO SS, and CISO-TF. So we have an ID number, which is referred to by the ASE controller, and then TFI lists out the identification numbers of the CJunct, MIMO SS, and CISO-TF cards. The PLTBODE card requests the Bode plot output. So we have an ID number. Next, IDCMAR is the identification number of a CMARGIN bulk data card. FMIN is the lower end of the frequency range for the Bode plot in radians per second. Fmax is the upper end of the frequency range for the Bode plot in radians per second. NF is the number of frequency points between Fmin and Fmax, including both ends. Log scale is a flag, so for log scale equals 0, we have evenly distributed NF data points between Fmin and Fmax, and for log scale greater than 0, then the NF data points are evenly distributed in the log scale. File name is the name of the data file, and then lastly, draw is another flag. If draw equals 0, the diagram of the Bode plot is not printed out on the standard output file, which is the default, and if draw is greater than 0, then the Bode plot diagram is displayed on the output file using ASCII art. So remark 2 here, the data file is in TecPlot format, where each zone consists of the data for the open-closed system of each gain connection element at one pair of density and velocity. And it's important to note that the generation of the Bode plot requires additional computation time, especially for the frequency domain ASE analysis. So be cautious with the choice of the NF value because the computation time scales linearly with the choice of NF. So we'll look at some quick examples here. So we have an open loop and closed loop ASE stability analysis of a generic advanced fighter aircraft GAFA with stores. The purpose here is to demonstrate the open loop Flutter analysis of the GAFA plant model using the frequency domain and the state space approaches in the ASE module. We're going to demonstrate how to build control systems in the ASE module and demonstrate closed loop Flutter and stability margins analysis of the GAFA using the ASE module. So on the left-hand side here we have the structure model, on the right we have the aerodynamic model, and then we have two control surfaces which will be used as input. We have an inboard aileron and an outboard aileron. The actuator transfer functions are shown here. So we have the inboard aileron on top here, and then the outboard aileron transfer function here. So the executive control section is shown first. We're importing the Nastran solution GAFA.FO6. Print is 0. The format's MSC Nastran. The boundary conditions are anti-symmetric. Support is -246/88888. So we have 3 anti-symmetric rigid body modes. The minus sign triggers ZAERO to clean up the rigid body modes, and then the /888888 tells ZAERO which grid point to use as the reference point for the rigid body modes. Additionally, we're importing the MGG matrix using the assign matrix executive control command. So next we have the case control section. We have a title. We have echo equals sort, so we will output the input cards onto the output file, which I like to do so that my output file is self-contained. You can see what the ZAERO input was for that particular output file. We have 5 subcases defined here. Subcase 1 is the open loop ASE analysis for the plant model by the state space method. Subcase 2 is the open loop ASE analysis for the plant model using the frequency domain method. Subcase 3 is the closed loop ASE analysis with a Flutter suppression system by the state space method. Subcase 4 is the closed loop ASE analysis with the Flutter suppression system by the frequency domain method. And then finally, subcase 5 is the closed loop ASE analysis with the same Flutter suppression system using the state space method, but instead of CISO control elements, we're going to combine all of the control elements, which we'll see, into one single MIMO control element. So this is the interrelationship of the bulk data cards for subcase 1, which is the open loop ASE analysis. So our ASE card here refers to an ASE controller, which only defines our control surfaces and sensors. The remaining fields are blank, so this is an open loop analysis. The ASE card in the RAA ID field refers to the MinStat card. So IT max is 100 here, so we're using the modified minimum state method. We have 14 lag roots, and then we're specifying approximation constraints here. So DA0 equals 1 imposes A0 equals QHH of 0, and then DA1 equals 2 imposes the imaginary part of Q at the first non-zero. What's going on here? Sorry about that. Okay, we'll just roll back a little bit and splice together, Shannon. DA1 equals 2 imposes the constraint, the imaginary part of Q at the first non-zero reduced frequency must equal our RFA parameters. And this is done so that the smallest reduced frequency corresponds to the aerodynamic damping derivatives. Going back here to the left-hand side, our surf set defines 2 control surfaces, the outboard and inboard ailerons. So that refers down here to the AESurf Z cards. The AESurf Z cards refer to the actuator cards, so these define the actuator transfer functions. Our SynSet lists 1 sensor, so we have a roll rate sensor at grid point 20,059. So we're using the ASE sensor 1 option, which, if you recall, I said is the easier card to understand. So you can see right away this is a grid sensor. V is rate or velocity, and then R1 is the rotational. So we're doing the rotational grid rate about the local x-axis of grid point 20,059. And it's important to note here that the axis definition is in the grid output coordinate system. So remember, from Nastran, you can define a coordinate system in which the grid is defined, and then you can also define a coordinate system in which the grid output, or the eigenvector, is defined. So this sensor uses the output grid local coordinate system. Next, the ASE card refers to the Flutter card, which defines the flight parameters. So we have antisymmetric, boundary condition. The M-list here refers to a set1 card, which deletes the side translation and yaw rigid body modes, but we're keeping the roll rigid body mode. So we're excluding modes 1 and 3. And then we have the rigid body reduction card to clean up the aerodynamics of the rigid body roll mode. So we have 4 in the component number here. So now we have the output of the RFA. So this is a copy of the output file. So you can see here ZAERO is telling you how many modes we have. It's 28. We have 28 because remember we deleted 2 rigid body modes from the 30 original modes. We have 2 control surface modes, ZAERO gust and ZAERO component load modes. And then this is a plot of the convergence. You can see we have very quick convergence, which is typical. And then it quickly, after only about 10 iterations, the solution converges, but we have 100 iterations shown here. This is very fast, so specifying 100 is fine, even though it looks like within about 10 iterations, it's already converged. And then lastly, ZAERO tells you at the bottom here we have 0 eigenvalues for the rigid body mode 4 was enforced according to the bulk data card RB read. Also, you can see the approximation constraints were output here. The arrow lag roots are printed out here. Next, we'll look at the state space construction. So once again, this is copied from the ZAERO output. So our Aeroelastic model is EXTOUT equals AX plus BU. So our XAE consists of 56 structural states and 14 aerodynamic lag states. The output equation has 1 sensor. The actuator model, we have 6 actuator states, which are coming from 2 control surfaces. So here's our first control surface and transfer function. Our second control surface is the inboard aileron with its associated transfer function. We have 0 grid point forces. So the plant state space model has 76 states, which is 56 plus 14 plus 6. Now, solving the eigenvalue of the plant state space model at a set of density and velocity pairs specified by the fixed Mach card yields the VG and VF diagrams shown below here. Now these diagrams can be generated from the output file specified in the plot VG card. So we have a vgplot.exe code, which is available in the miscellaneous subdirectory of the ZAERO installation path. Also, if you're like me and like to use MATLAB, you can email me or email support at zonatech.com and ask for the MATLAB codes. Also, the vgplotter, I believe, is vgplot.m is available in the miscellaneous subdirectory as well. So the vgplot is a standalone Windows executable. The MATLAB script obviously requires MATLAB, but they both generate similar plots. So here graphically we can see we have an unstable mode right here. So we have a flutter mode right here. This is mode 2. And if we come over and look at the frequency, we can see the frequency is about 6 Hertz. Between 5.5 and 6 Hertz here is the flutter frequency. The dynamic pressure is around 10 or so. And I'm not sure the units, what our units were. Must be PSI. So here we have a flutter mode animation. Next is the second subcase, which is the frequency domain approach of the open loop GAFA. So all of the input bulk data cards are identical to those of the first subcase, except the min-stat card is not required and the rigid body reduction card is not required. So the results of subcase 2, you can see the results are very similar, which indicate that our state space rational function approximation had good parameters, because you can see the shape here of this mode is very similar. And then if we compare the flutter results, our flutter dynamic pressure for the frequency domain approach was 11.3 psi, and the state space approach was 11 psi. The flutter frequency in the frequency domain approach is 5.8 Hertz, and the state space approach is also 5.8 Hertz. So we have a suitable RFA parameters here. So let's move on to the closed loop analysis. So we're going to use the state space equations of the plant model generated from subcase 1 via the ASEGAIN card and export that plant model into MATLAB. And then we designed a flutter suppression control system. And that's process isn't shown. We're just going to show you the designed control system. So this Flutter suppression control system consists of one low-pass filter, 3 phase lead compensators, and 1 notch filter, and their transfer functions are shown here. So we have a low-pass filter, we have the notch filter, and then we have 3 phase lead compensators. So the notch filter, low-pass filter, and the 3 phase lead compensators are specified in the ZAERO input deck by 5 CISO TF cards with IDs 209, 210, 211, 212, and 213. So the notch filter is shown here. So if we go through the card here, so the numerator and denominator are both second order. So our and the numerator and denominator are both 2. And then going for the denominator first, our coefficients are 1024 and 64. If you recall, for the CISO TF, the coefficient on the denominator here must always be 1, so it's excluded from the definition here. For the numerator, we have 1024, 0.32, and then 1. So the numerator coefficient on the highest order term must be specified. Let's do one more example, the low-pass filter. So the denominator is order 1, the numerator is order 0. The denominator, our coefficient is 4.8, and then for the numerator, the coefficient is 4.8. And we have a similar thing here for the 3 phase lead compensators. Next, we have a C-junct card, which has 1 input and 2 outputs, which is used to connect the output of the Flutter suppression control system to the 2 actuators. So note here that the sign feeding to the inboard and outboard actuators is opposite. So the 2 actuators are actually going to be moving in opposite directions. And then the magnitude is different. So U here's the output of the Flutter suppression control system, and then Y1 and Y2 are the control commands to the 2 actuators that drive the control surfaces specified by the Aeserv bulk data cards. So this C-junct card is shown here. So the number of inputs is 1, number of outputs is 2, D11 is 0.0333, D21 is minus 0.25. And this is the interrelationship of the bulk data cards. So we've come down to our Flutter suppression control system. We have the ASE sensor, which is connected to the CISO TF card via an ASEGAIN card. So we're going to, we have a GAIN connection here. Then these 5 CISO TFs are the 5 transfer functions we've just seen. So those are all connected to each other via the fixed connection cards. And then lastly, we have the C-junct card. So the last CISO TF has a fixed connection to the C-junct. And then the output of the C-junct, remember we have 2 outputs, are connected to our 2 actuators via the 2 fixed connection cards. So meanwhile, the ID numbers of all of these cards must be specified in the TFSET, GAINSET, and TFSET cards. So the ASE card, or the ASE controller card, refers to the TFSET, GAINSET, and TFSET cards, and these cards list out the ID numbers of the control elements. Meanwhile, we have a CMARGIN and a PLTBODE card activated in our input. We have a variable gain shown here. So the gain value specified by the ASEGAIN card has a variable gain schedule that varies with the air density according to this figure. So we're scheduling the gain value based on density. So at lower densities, we have a fixed gain of 1. And then as the density increases, we ramp up the gain quickly to about 4.5. So we're really driving up the action of this controller. And then as the density increases further, we go lower in altitude, higher dynamic pressure, then we drop the gain off. So we taper off the action of the controller. So here's the ASEGAIN card. So we have a table D1 card to define this plot here, and then it's scheduled on density, as shown here. Next, we'll look at the CMARGIN and PLTBODE cards. So the CMARGIN card specifies the upper and lower gain margins to be 50 dB and minus 50 dB, so that's where it's going to search for the gain margins. And in the phase margins, it's going to search within plus and minus 60 degrees. The PLTBODE card refers to the CMARGIN card, which will output the Bode diagrams. The frequency range is between 5 and 70 radians per second, and it has 51 frequency increments. And then lastly, the PLTVG card outputs the VG plot to the file VG closestae.dat file. So similar to the open loop state space approach, the state space approach for the closed loop GAFA first applies the RFA to the generalized aerodynamic force matrices due to structure modes and due to control surface kinematic modes using the modified minimum state method with 100 iterations. Then the RB red card is activated to clean up the rigid body submatrix corresponding to the roll mode in the A0 RFA matrix. So now we'll see how the state space equations are modified. So our difference here is now we have a control system states. So we have 6 states coming from 5 CISO elements, 0 MIMO elements, 1 junction element, 7 fixed connections, and 1 gain connection. So of course all 6 states are coming from our 5 CISO elements. So the closed loop state space model now has 82 states, which is the 56 plus 14 plus 6 coming from the open loop model, and then our 6 control states, which gives us a total of 82 states. Now solving the eigenvalues of the closed loop state space equation at a set of density and velocity pairs yields the VG and VF diagrams. The damping curves below are all below the zero damping line, indicating that flutter instability is suppressed by the flutter suppression control system. So this mode you can see gets really close to 0, but doesn't quite cross it. So our flutter has been suppressed using the flutter suppression control system. So next we'll look at the gain and phase margin results. The margin analysis, remember, was activated by the CMARGIN card. And the typical output for the margin analysis at an dynamic pressure here of 12.938 psi is shown below. So this table shown here will be repeated for every dynamic pressure that you have in the analysis. So if we look at our positive gain margins, the smallest positive gain margin here is 2.6 dB, so that's quite small. The smallest negative gain margin is minus 3.5. So because we have a negative gain margin, this dynamic pressure is actually past the open loop flutter, but our controller is suppressing flutter. So we have a stable system, but if you take away the controller or you reduce the gain on the controller by 3.5 dB, then the system would become unstable again. If we look at our phase margins, the smallest positive phase margin is 20 degrees, and then the smallest negative gain margin is minus 95 degrees. So now we'll plot the gain and phase margins. We have 2 gain margins, one around 330 radians per second and the other one around 100 radians per second, and then 1 phase margin whose cross frequencies consistently appear in the whole dynamic pressure range. And at a dynamic pressure of about 13, 14.5, and 17.5 psi, the gain margin results show that the closed loop GAFA model has insufficient gain margin if our gain margins would be, for example, plus or minus 6 dB, which is fairly typical. In addition, the phase margin is infinity when the dynamic pressure is greater than 17.5 psi. So for this particular cross frequency, these are our gain margins. So this is all, so these 3 right here is about 5 or 6 dB. For this particular cross frequency, these are our gain margins. So once again, this is very small gain margins. And then our phase margin analysis for this cross frequency, you can see that at these 3 dynamic pressures, we have a very small phase margin. Next, we'll look at the output of the PLTBODE card. So these are the Bode plots for 2 different dynamic pressures, 2.67 psi and 4 psi. So we can see the magnitude in phase here from the Bode plots. Next, subcase 4 is the frequency domain approach. So this is identical to the state space approach, except once again the MinStat card is not required and the RB-Red card is not required. And we'll look at the VG and VF diagrams. Now, because the frequency domain approach does not involve the RFA, the frequency domain closed loop model has only 56 structural states, 6 actuator states, and 6 control system states. So the total number of states is just 68. It does not have the aerodynamic lag states. And the G method's applied to obtain the damping and frequencies of the 68 states at the 13 density and velocity pairs. And the results are shown here, which look very similar to our open loop analysis. Or our, sorry, not our open loop, our state space analysis. Now if we'll compare the frequency domain and state space analysis gain margin results, we'll do that here. So the gain margins and phase margins versus dynamic pressure computed by the frequency domain approach compared to the state space approach is shown. So these 2 approaches yield similar results, which indicates that we have good RFA parameters. And then next, the PLTBODE results are shown below here. And then lastly, we're going to do the state space approach, but using the MIMO controller. So here we take out those 5 CISO TFs and replace them by 1 MIMO SS card as shown here. So you can see here that our input becomes much simpler because now we just have an ASEGAIN card connecting the ASE sensor to the MIMO SS, and then the MIMO SS is connected to the 2 actuators through the 2 fixed connection cards. So our MIMO SS is shown over here. It has 1 input and 2 outputs with 6 states, and it's converted from the 5 CISO TFs and 1 C-Junt card used by the 3rd and 4th subcases. So our ASE controller, now the TFSET card only lists 1 control element, which is the MIMO SS. So the MIMO SS here, we have 6 states, 1 input, 2 outputs, and the matrix name is MIMO. And so in this instance, we've used the DMI cards in ZAERO to define the ABCD matrices in the input itself. Another option would be to use the assign matrix executive control command to import that matrix from the output 4 definition. The state space equation of the MIMO controller is of the form EXTOUT is AX plus BU, and then Y equals CX. Our D matrix is just 0. There's no direct feed through. Our A matrix is shown here. Our B matrix is here, and then our C matrix is down here. So the result of the 5th subcase is identical to that of the 3rd subcase, which demonstrates that the Flutter suppression control system can be modeled either by a set of CISO control elements or by 1 MIMO control element.